degraded. And it can basically come from being inside the soil, so that once I put everything inside and it vanishes or perishes. The other aspect of biodegradability also comes from what we call bioresorbability, meaning that the material is resolvable inside the human body. So if I put electronics in human body, and if its nature is transient in nature, that means it's required to do a job for a certain amount of time. It might be 1 week, 1 month, or one year. After that, the electronics should not be there in the human body, and it should be reabsorbed. And that's what we are trying to produce, so that we can make these bioresorbable and biodegradable inks, and then print them to make new kind of sustainable electronics for the future. When it comes to the materials, I'm sorry, my cursor is, my mouse is giving me a headache right now, but it's okay. When it comes to the material innovation, we are primarily looking into the polymers. Polymers we are investigating are PEDOT and PVDF based. PEDOT based materials are known for their biocompatibility, so they are very good candidate for next generation healthcare devices. And the idea here is to increase their stretchability, increase the conductivity of these materials so they can be put on different surfaces. PVDF is a piezoelectric material, and it has great sensing capabilities. But again, it is not biocompatible in nature. And what we are trying to do is basically manipulate the polymer chains of this material to not just enhance its piezoelectricity, but also to make it more compatible for the human body in that sense. And when we are working, as I think Geese has already shown it with on-skin surface electrodes, that the ones that are already available have a lot of issues where they give skin irritation, they can dry out. The whole idea of converting these materials into on-skin applications is also to make sure that we do not have any of skin irritation kind of issues in these materials. So we try to play a lot with non-toxins or materials which do not have any harmful chemicals in them. At the base, when it comes to the core scientific explanations and investigating, we are also dealing, as I said, with a lot of process optimization in our lab. Now, when you talk about new materials that you are making, the new inks that you are making, and also the new substrates that you're working with, there are a lot of issues that can come forth. Well, it might, to a person, it might sound very easy that you have a material, you have an ink, and you have a printer. And the moment you combine them, you can have a good design. It's never as straightforward as it sounds. We deal with a lot of issues, one of the most common being the coffee ring effect, wherein what happens is, just like your coffee mug, most of the material basically transfers and gets collected at the rim rather than at the center. So there's no homogeneous distribution of the material once you print it. The other issue is alignment. Sometimes the alignment of the materials, for example, carbon nanotubes or graphene sheets, gives you better electronic properties and enhancement of functionality, which is not achievable or which gets destroyed when you're trying to print them. And we have been looking into material alignment, evaporation dynamics, surface tension issues, ink-substrate interactions in order to understand what should be the right recipe for a particular ink on a particular surface to evade this kind of issues that we face. Now I will take you through some of the case studies and interesting projects that we have been doing in our laboratory. One of this project that is something that I picked up when I was doing my postdoc in Singapore, and it was just out of fun and curiosity that I started to look at various textiles, and the aim was to basically print directly on these textiles. And as you know, we have a huge range of textiles available to us, from wool to fabric, woven, non-woven, net. And there is no one recipe that basically gives you the solution. And sometimes some textiles will require pre-processing, some of them will require post-processing. The idea, however, is to get somehow the ink sticking to your surface. What came out of this study is a very interesting fact, which was that some of these inks adhere very well to some of the surfaces or textiles in a way that enhances the functionality. So if I were to print the same material on a glass or a plastic, they might have a certain, for example, sheet resistance or a conductivity, but that gets enhanced when I put the same material on a textile. It's because the ink substrate adhesion is very good, which provides a very homogeneous and continuous path for the electrons to flow. And that basically led me to take up a project which we have just recently concluded. So this is in conjunction with the collaboration with Bispia Hospital in Copenhagen. The idea here was to put these muscle stimulating electrodes on a healthcare textile. Why do we need such kind of garment? Is because when a person is lying in ICU, the first thing that happens when a person is bedridden is loss of muscle mass. They tend to lose their muscles, and it can be as high as 50 to 70%. And that leads to weakening of the whole immune system and the body. The way to treat this whole thing is that once the patient is discharged from the ICU or the hospital, they go to a specialist where they put these big bulky electrodes and they start to stimulate these muscles. There are a lot of scientific and clinical findings saying that if you stimulate the muscles while the patient is in ICU lying on the bed, then you can help improve this muscle wastage. And this is exactly what we did in this project. So what we basically did was we made our own biocompatible electrodes. It's a 3-layer electrode system that we made, and we directly printed into a compressive stocking, which is a textile commonly used in hospitals. It's mostly worn by the ICU patients. And then we connected the wires to it and to a stimulator. The first prototype that you see here has wires, dangling wires, which is not good to look at, but we already have a second prototype now where we have also printed the wires. So you can see that it's just like a normal stocking a patient is wearing, and he and she can stimulate herself for 15 minutes. And we now have collected clinical data. We have clinical evidence now where you can reduce the muscle wastage to about 20%. So this is, I mean, something of a, because I get a lot of questions that why do you want to even print on textile? So this is just a good example of that. A fun project can basically have a very good application in healthcare system. The other of my passion projects is that I would like to combine what I call as biology with electronics, and that's the new growing field of bioelectronics. Bioelectronics is not new. It's bioelectronic devices have been quite well used and successful in biomedical industry. Well, whether it's a pacemaker, your hearing implant, etc. The problem comes if you have to use these for a longer time, because that leads to scarring of the tissues and bloods and bleeding, etc. And the idea moving forward is, again, to have more skin-like devices or electronics going inside the human body, which have Young's modulus, which matches of the human tissues. And in this project, what I wanted to do was first investigate that can we first make any biocompatible inks which can survive alongside with cells and tissues. B, whether we can actually, if I make an interdigitated electrode or if I make a heater, what would be this kind of environment provide conducive environment to the human skin cells so that they can survive, or whether they will die. So this is exactly what we did. So we 3D printed a hydrogel patch. Hydrogel is a very successful material already used in tissue engineering. And then we printed, and we first of all made our own materials, which do not need any post-processing. So the moment you print this silver material, it's good to go. And then we sandwiched it on another hydrogel layer and made a patch out of it, which was then used for biocompatibility studies with mouse cells and human skin cells. The idea was, again, to look what kind of voltages can we give to human skin cells, what kind of heating temperatures can we give to the human skin cell so that they survive, and whether there is any proliferation of the cells or not. And this was a proof of concept and a successful study. So the answer is yes, that it is totally possible to combine biological aspects and species with electronics moving forward. As I said, we are also big into the biodegradability aspect of the materials. And it's not just in terms of biodegradability in the environment, but also bioresorbability in the human body. The idea here is that, as you can see in this picture, what you can see here is a PLC material. It's a polymer material. Again, it's a very famous tissue engineering material, which is commonly used for muscle tissue engineering in biology. And what we did was we used carbon nanotube as the ink, and then we printed an antenna design onto this material, and then tested it. The final investigation was that if I were to put this whole printed PLC material into the same environment as a human body, which is 37 degrees centigrade with a certain amount of oxygen and carbon dioxide, what happens to it? And we found out that within 1.5 to 2 months, everything completely degrades. There's nothing left. And the right application for this kind of a work would be that if we can have electronics going along with the implants, then the doctors can actually have a relay of information that how the implant is doing inside the human body. Because right now they have no way of knowing. They just do the operation, they put the implant, and then they wait for the patient's body to whether accept the implant or reject it. They have no investigation there. However, as I said, if you were to put electronics with the implants, the idea is that they should relay the information for a certain amount of time. But once the implant is successfully accepted, you don't need that electronics there. And after that, the electronics should be completely reabsorbed inside the human body. And this is what we have shown, that this is totally possible with certain materials and combinations. This is another area where we have, again, it pertains to wound management. So I do a lot of work with wound management because when it comes to wound management issues, whether it's detection of the wounds, management of the wounds, or treatment of the wounds, there has been no innovation. And the usual way for doctors to do it is basically unwrap a bandage and look at the wound and then treat it. They have no way. And this is okay for acute wounds, that's fine. But when it comes to chronic wounds, which are old, which are more painful, the whole bandage, unbandage process can be very painful for the patients. So what we are trying to develop in our laboratory, as you can see, are on-skin patches for the near wound sites, which can give us an indication of how the wound is doing. Now, that indication can come in the form of changes in the pH, changes in the temperature that we can detect, change in the oxygen levels that we can detect. And that's the array of devices that we are trying to build in our lab using printing technique, because the whole idea again is not to have too many wires, not to have any hard components, and not to have any materials which might be toxic, because we are talking wound. It's the most sensitive site on the human body. And this is what we have shown in one of the projects here. In another project, this was again a project that I completed back in Singapore, where the idea was to, with a doctor, where again, it has been clinically shown that if you have some kind of heat signature or some kind of electric stimulation at the wound site, then the wounds tend to heal faster. So the idea was you get these $2 and $5 plasters in the market, right? And they are chemical in nature. You put on your wound or bruise and then they tend to heal. Is it possible to print electronics on these plasters so that we can get some kind of a heating or maybe some kind of electric stimulation? Now, printing is one part of the story. Yes, we can print. That's not a problem because it's a smooth surface. It's a polymer like a plastic sheet. The problem comes from the fact because these are low temperature substrates. Most of the time when we are printing electronic inks, we need to have some kind of post-processing. Most of the time, this post-processing is a heat treatment, which is somewhere between 100 to 200 degrees. These substrates cannot withstand that temperature. And that is a problem. So what in this project we did was investigate into laser sintering as a means of post-processing so that we could only sinter the tracks that we printed without damaging the underlying substrate. And what we basically have shown as a proof of concept here is that it is totally possible to print and functionalize the inks onto these plasters, and then you can get like an actuation motion out of it, and you can detect the motion of the wrist, for example, in this case. So I think this is possibly the end of my presentation. So what I want to leave you all is with a message and the idea that there are infinite possibilities available to us when we think about putting electronics where as of today, it does not belong. So we would want to convert a redundant surface like a car seat or anything like a tabletop into having an electronic functionality. And then that basically opens up new avenues to have new kinds of form factors and design innovations. Smart textiles would, I think, would be a huge market moving forward, because we are looking into putting all the devices that you carry literally being embedded into your textiles, and that creates a whole new ball game for new age wearables, which are not hard and which are free of any wires and so on and so forth. So that's very much from me. Thank you so much for your patience and listening.
Okay, let us have a time for question and answer, and any comment is welcome. Then, would you please comment on the promising opportunity of a printing technology toward future flexible electronics?
Yes, so I think as we have already seen some of the talks, I mean, the promise is huge, and whether it comes to embedding electronics directly, which I think Professor McDonald's is doing or Jennifer Lewis is doing, or whether it's directly printing on these surfaces, which I think a lot of people are doing. Um, I think the only challenge comes from the fact of reliability and repeatability, because sometimes printing processes and the inks that you produce, because these are in-house inks, they might not be very reproducible. So there might be variations from batch to batch. And I think if you solve these issues and you create the right library of materials, I think then it's basically game forward, where you can create a lot of new age devices.
Okay, then what is the most biggest issue for toward future flexible electronics?
As I said, I think the biggest issue is, for me, I would say it is the range of materials. We don't have all the materials. So if I say that right now, I don't think so that printed electronics will overtake the modern manufacturing, traditional manufacturing technology, because we are not there in terms of processing speed, in terms of the cost, in terms of the materials. If you have to replace all the whole PCB that we have right now with the printed one, you need a whole range of materials. And it's a little difficult, because sometimes you get the right materials, but that they are not printable, or some materials which are printable do not have the right functionality. So it's always a balance that you have to find, and you have to keep on building that library of materials. And then of course it all comes down to the cost. As we have discussed, the cost when it comes to 3D printing per piece is quite high. And unless we can reduce that, commercialization would be very difficult.
Okay, and any other question or any comment? Then I think since there is no more question,
There are
so
some
I
questions
think
in the chat.
uh,
There are some questions in the chat.
okay, please go ahead.
Okay, maybe I can read then. What is the order of conductivity that the mentioned modified PEDOT ink has reached? Could it be suitable for RF applications at gigahertz? No, I do not think so. It would be, I don't remember the values, but I don't think so we can reach the gigahertz values as of now. But if I remember correctly, there is a group, I don't remember where, they did publish a paper on some high frequency application of PEDOT, but I don't remember. They did some modification to the PEDOT, so maybe you want to look at that paper. But for this material, no, we are not looking at that. What is the conducting material for realizing the biodegradable antenna? So I used carbon nanotubes in this case. It's a standard carbon nanotubes. Uh, and how does the device deals with the communication issues inside the human body environment? Well, that's a big challenge. I completely agree. We did not test it. We did not do any in vivo studies where we put the device inside a animal model and test it. And that would be an issue, because then you are talking about communication distance and all those things. But that's another challenge to overcome. The first challenge was to realize whether we can even do that. And that's what we did in this study. So maybe the next step for us would be basically to go into that field of putting it aside, having an animal model to test it and see what would be the communication issues that we feel.
Thank you very much. Answer.
And do you have plans for upscale commercialization of these? Well, I can only tell you about one of the projects that we did with the Copenhagen Bispebjerg Hospital. Yes, we do have plans for upscale and commercialization of those healthcare solutions, and that's in the pipeline. But the rest, I would say it's a low TRL proof of concept work that we are still trying to do.